Okay, so this video is the first video in a new topic, which is optimization. And what the rest of the course is about is really applications of derivatives. So we all, we've done this, right? So we've got this big, nice chart of derivatives, of derivative rules. And, it's a sort of nice just exercise, I guess, to do these, but it's kind of dumb to just do this thing called a derivative unless there's maybe something that this really actually has an application for, or in other words, something that, a real life problem that I might actually encounter that I want help finding a solution to. That's sort of what hopefully math is all about. And in in reality, no, you're not walking down the street and you see, ln of x squared plus 1, and you're like, oh, gee, I wonder what the derivative of that is. Like, I mean, nobody cares about that. So, but if it came up in a application of, I'm trying to build this bridge, and I'd like to know how long this piece should be in order to make it the strongest bridge possible. Oh, okay. Well, that's something that probably should and does matter to you and me. So anyway, so armed with this chart, right, and our knowledge of what a derivative is and how to do it, and hopefully how to do it quickly at this point, we're kind of hopefully at the point of being able to not get fouled up on just basic derivative things. Maybe, we still need the chart and we still need some help on harder derivatives, but armed with this anyway, what are some things we might use the derivative to actually help us solve and to actually help us do? And so anyway, back to this. So optimization or optimization problems are one of the applications that a derivative is helpful for. And in fact, with real world problems, i.e. word problems, we can use just a basic application of what a derivative does for us to very creatively, I would say, and sort of ingeniously in some ways, solve some problems that you really don't have any other, you would really be very hard pressed to solve in any other way. So, okay, and this is real. I mean, people really do use derivatives to solve problems like the ones that we're going to eventually get to in this section, in this unit. So, okay, so what is optimization all about, and how do we do this, and all that good stuff? So first, just a sort of general idea of optimization. What does that word even mean? So I think it's just a word in English, right? So of course, and in math, it's going to mean the same thing. So optimization, what is this topic? So so when we have some function or quantity a useful question and a useful answer to that question is where does this function have its maximum and maybe sometimes minimum or minimal value? Oops. Okay, so just what is optimization in general? I think just in English, optimizing something, I think just kind of means to make it like the best, right? And I think that's what optimizing means. You're optimizing your vacation if you do a lot of really fun things in it, as opposed to just sitting in the hotel room like watching TV. Okay, so it's just a regular English word that just kind of means to make best or make most good, whatever good means to us. And it means the same thing here. So just to sort of apply it a little bit more to science and to math, it might be that we have some quantity, some object, some thing that we're studying, some quantity, and maybe we have a function, just with x's and stuff in it, that represents that quantity. And we want to ask the question, okay, if I have this function that maybe represents the cost of operating a company, for example, it might be nice to know the answer to the question, okay, if I have some function that represents the operating expenses, right, the cost of operating my business, how much product should I make in order to minimize cost? That's a perfectly reasonable question, and one that you as the business owner would probably like to know the answer to. Anything, right? You can think of a lot of things where you're saying basically you're trying to either figure out when is some quantity made biggest or smallest, depending on what's good for you. And you want to know, you want a scientific way of figuring out, how do I make this quantity as big as it could possibly be or as small as it could possibly be? That's what optimization is all about. So a reasonable question to ask is this, right? Where, and when I say where, I mean, for us, tell me either on a graph, if you want to physically talk about graphically where is this, or, algebraically, tell me what x value gives me the largest y value, or smallest y value, or lowest, if you want to say that too. So that's what these optimization problems are going to be all about. And we're going to do a variety of problems, of word problems mostly. We'll start with some non-word problems just to get the strategy established. But once we establish our sort of general idea or of how we're going to do these problems, we're going to move just into word problems where it's, here's a situation and here's a setup, and you need to be able to make this thing the biggest it could possibly be or the smallest it could possibly be. And that's it. So, okay, so so we need a strategy, right? As per usual, I'm kind of just going to sit here and kind of say, well, I don't know how to do this. If you want me to say, so maybe I'll just say, so for example, for the function, x squared plus 2x minus 3. What x value gives you the largest y value, right? I could plug in anything I want in here for x into this function. And, if I plug in x equals 1, for example, I get 0. That's probably not the answer. If I plug in x equals 2, I think I get 5. Okay, well, maybe that's the answer. Well, I don't know, because maybe I could plug in something else and get 10 or 20 or, who knows, right? So guessing, as I've just done, is obviously bad, or certainly that's a bad strategy. It's not really even a strategy, guess and check. So I need some smarts. I need to apply some sort of a strategy here to do this. But this is the type of question that we want to be able to answer. And again, probably not so much just a dumb question like this one, which is just like, well, who cares, right? But if f of x, if I say x is the grade you're going to get on a test, I'm sorry, if x is how long you study for a test, and f of x, or y, if you want to say y, is your grade on a test. Oh, well, now all of a sudden this maybe matters a little bit more to us, where I'd be asking the question now, tell me what x value gives you the largest y value. Oh, well, in this setup it would be, tell me how long do I study to get the highest grade on a test. Oh, that seems like a good question, very timely question that we might now want to know about. So I say, okay, well, if this function represents my grade on a test for studying x hours, well, this is I don't know exactly how I would know what that function is, but okay, well, let's play along with me here. Then, okay, this is a reasonable thing to maybe want to know. All right? So, and we'll have, like I said, probably more realistic word problems shortly. But, okay, so how do I even approach doing this, right? I know nothing, really. I have nothing to really say about this. So let me pull us back a step or two and say, all right, well, if I'm trying to find where a function or quantity has its highest and maybe lowest possible values, or its maximum and its minimum, then okay, well, what possible strategy would I have besides just sort of checking, right? I mean, it kind of seems hopeless unless I have some idea that might, do this in a smarter way. So let me just draw a picture for you. So imagine you have the graph of just a random function. Of any function you can think of, any random f of x, whatever you've got. Imagine you made a graph of it, and I'll just sort of make something up here for us to look at. So let's say it goes something like this, and then maybe something like this, and I don't know, down there. So I wanted to make that a little higher. Sorry about that. Okay, so whatever sort of squiggly type thing you just make up, that's fine. So let's say I'm living in this world. So I'm going to I don't usually do this on a graph, but let's just say I'm kind of living in this world from A to B. Okay, so in other words, just this window here that you see of the graph. Okay, so that's just a random, I have no idea what the equation of that graph is, but who cares, right? It's just a random function, and you can draw any graph of any function, so you can always do this. All right, so here's a picture we've got. Now, if I asked you, and you can all do this on your screens right now, to circle for me, come over here to the graph, and circle for me, where does this have its highest value or its maximum value, and where does it have its minimum value or its lowest value? I have faith in all of you that it shouldn't take you more than about 2.5 seconds probably to come up to the screen here or come up to the board, and you would say, well, where does this function have its highest or its maximum value or its highest value? Well, I don't know. I mean, just sort of using my eyes and my brain ever so slightly, there-ish, right? Somewhere around there. That's where it has its highest overall value, for the simple reason that I just looked at it, right? I mean, right? And by similar logic, where does it have its overall lowest or smallest value or minimal value? Again, by the same just non-scientific argument, that looks like it's maybe where it has its smallest possible value, right? So I might come up here and I'd say, so that's the smallest, that's the max and the min, or the biggest and the smallest, or highest and the lowest, whatever you want to call it. And, I'd be sort of done, right? World's easiest problem, I guess, right? If I gave you on the next exam just a bunch of pictures like this and said, circle the highest and lowest, well, you'd all, I think, get 100, right? And that's good. I mean, in the sense that this is not that hard for a human that has eyes to do, because you can just look, right? Or if you have a picture of the graph, I should say, or if you have a picture of the function of graph, it's not hard at all, because you just look and say, well, geez, there it is, and there it is, and that's the end of the story. So, okay, so what made this so easy for us as human beings to do? Well, we had a picture, okay, but even aside from that, what made it easy? I'm guessing, I don't know how you answered that question a minute ago, but I'm guessing you didn't obsess a whole heck of a lot about, let's say, points that were sort of in this region. Why? Why didn't, or maybe you did, but hopefully you didn't, but why didn't you, really contemplate, oh my gosh, maybe that point's the maximum or the minimum, or maybe it's that one, or how about that one, or that one? I'm guessing that your eyes sort of immediately went to the top there, the peak, right? The sort of peak of this mountain, so to speak. And you probably didn't obsess too much about points like that, right? Ditto for, points like these guys, right? You probably just were like, I don't even care about those guys, right? But again, let's just think a little bit about, why don't we care about those points? Why don't I have to sit here with a ruler and a protractor and stuff, and why don't I have to look at those guys and say, oh geez, I don't know, these guys could be the highest points, or one of these guys could be the highest, or one of these guys could be the lowest. We're going to give a sort of, mathematical explanation. I think a reasonable explanation would be, let me just take one point in particular, that one, let's say. Why don't I think I have to worry too much about that guy being a maximum or a minimum? Is because if you look at that guy, doesn't he have friends, neighbors, really close by that are bigger than him or higher than him and smaller than him, right? So this guy, this one right there in the middle, he can't be the answer to the question, what's the biggest and what's the smallest, or what's the max and what's the min, because he's got neighbors that are above him and below him, which means he's out, right? He is not a candidate to be the maximum or the minimum. And ditto for all of these guys over here, right? These guys, the same story. So in fact, not to totally make what was a very easy 2-second question into a really long one, but what is it that I really actually would need to investigate? Well, none of these sort of, I don't know what you want to call these points, but in-between points, I guess, or something like that, none of those guys are going to be the answers to our question, what's the biggest and smallest? In fact, why were we able to maybe answer this question as human beings pretty quickly? Well, not only because we can sort of see this better, but even if we couldn't, what are the only real candidates for where the max and min could possibly be? Well, the max, right, again, I think we would all be in agreement, is right here, is right there, right? And what is so special about this point that I've sort of circled here is that is it not true that that is sort of at the top of a mountain or the top of a hill? And I'll go ahead and make it a little more calculus-y. What's special about this point that's maybe not true about all my other little blue dots that I drew in here and over there and pretty much everywhere else? Is that since it is at the top of a hill, the graph is flat there, approximately, right? So what's unique about my maximum, the answer to this question, is the slope is 0 there, right? It's flat, so it has a 0 slope there. And of course, slope is the same thing as derivative, right? So if I'm trying to sort of learn a strategy for how do I find maximums and minimums, it seems as though if I'm trying to kind of organize my thoughts, I might have some sort of candidates for the answer to the question, what are the max and what are the mins? Okay, and one candidate, right, in this case it turned out to be the answer, was this point here, at the top of the hill, and what was unique about that might be that it was a point where the derivative is 0. In other words, the slope is 0, right, or it's flat. So what's unique about that point is that the slope is 0 there, right, or the derivative is 0 at that point. And that proved, I think, to be an important player in this question, where does this have maximum and minimal values? Okay, well, is there any other point that has that characteristic? And you can pretty quickly scan the graph, I hope, and see that that's also a point there that has the characteristic that the slope is 0, right? It's flat there. Now, when you were scanning this, the maximum kind of probably jumps out at you, right? That probably was pretty easy to spot. But why wasn't the minimum maybe quite as easy to spot? Is because you probably had to do a little bit of a check here, right? And just sort of had to squint a little bit at it, because I hope you were maybe asking the question, which one is lower, that point or this point? And I mean, it doesn't take long to kind of see that it's the point at the end there that is lower. But this was at least a candidate, right? There was, I think, maybe, especially if I drew it a little bit, if I had shortened the graph a little bit and cut it off like there, let's say. Okay, then you might really have a debate, between which is smaller. But this was at least certainly a candidate to consider. Why? Because again, the graph is flat there. And at this point right here, whatever that magic dot is right there, why is he not like these guys and these guys? Well, that guy right there, over here, that point, yes, there are points near him that are above him, right? This guy has neighbors that are higher than him, but he does not have neighbors. And by neighbors, of course, I mean someone close by, right? He doesn't have neighbors that are below him. He is at the bottom of the hill, the bottom of the valley, right? So he is the smallest guy, smallest point, the lowest point in his sort of neighborhood. Now, this guy turned out to be the overall smallest, but at least in this local area, this guy over here was a candidate, at least, to be the overall smallest. Okay? So I guess I say that just to emphasize any point, right, where the derivative is 0 is at least a candidate for being the overall maximum or minimum. Okay? And again, none of those guys are. But these two, but this guy is at least there's a possibility. Now, why did he not turn out to be the winner or the loser? I guess if negative is bad, is because, well, this point actually, as it turned out, was even lower. Right. Now, what's unique about this point on the right, the one that turned out to be the minimum? Well, he's not one of these, right? The point at the end here, the answer to the question, what is the minimum? Well, the derivative is not 0 there, right? The graph is not flat, is it? It's sloped sort of downhill there, right? So there's a negative slope there. So that's not true. So what is unique about that point is that it's, I mean, this is probably not a very scientific process, right? But what is unique about this point? Well, it's at the end, right? So if I'm living in this world where whoops, what did I do? Where I'm living between, this A and B here. It's sort of like saying you've got blinders on, right? And you're just sort of thinking about the world between these 2 points. Again, I made all this stuff up, right? But you'll have real numbers and real problems to do this. But in this little world here, what's unique about the minimum that turned out to be the answer is it was an end point of the interval, so to speak, or in other words, it was at the end, one of the ends, either the beginning or the end of the region or the area or the interval that I was considering for this problem. So in that sense, this guy he actually did turn out to be the minimum, but he certainly should have been considered. And again, I think your eyes as a human being, I know we're into like 10 minutes on a problem that took 2 seconds for you to do. But just in analyzing what our human brains did for us is it probably said, let me find the peaks and valleys, and then let me also check kind of the ends. And then your brain processed and said, oh, okay, this end point here was smaller than this minimum over here, so that's the overall smallest. And then for the maximums, you probably maybe just for a moment, maybe not even a split second, at least maybe compared this maximum with this candidate over here, because that was also an end point. And you probably said, okay, but that's the winner. And that's the winner on the bottom side. And that was the end of the problem. I mean, that's pretty much it. Again, you sort of neglect all the other points. There are an infinite number of points on my graph here, and yet in reality, all I really needed to check were these 4 points. And by check, I just mean, plug them into the function, or in this case, since I have a graph, I can just look at it and tell me who's the biggest of all and who's the smallest of all, and that's the answer to the question, as simple as it sounds. Okay? So, let me write the other thing down, right? So candidates then for who might be my max and min. One candidate or one group of candidates would be any point where the derivative is 0, because those are my peaks and valleys, right? Okay? And these are, and then the other candidates are the endpoints. Okay, so which would have been this point, right, and this point. Those are the endpoints, right? Where does my graph get cut off, basically, right? Those are candidates, right? But look how, I know I haven't done a specific example here, and this is all just sort of generic, but as a process, this is actually pretty good. As long as I have a way of identifying all of the candidates, which I've made a list of them here, then all I really have to do at the end of a problem is say to myself, okay, so who's the overall highest and who's the overall lowest? And that's the answer. That's the answer to the question, where does this have its highest and lowest values? So what I really just need to do is be able to say, well, how do I know how will I be able to figure out this and this? And okay, so we need to think a little bit about that. But strategically, I hope it's clear, right, that when trying to figure out where is something optimized? Again, an optimized just means find the minimum or find the maximum, or maybe both, find maximum and minimum value. You really don't need to do a whole lot of investigation. The only points that are even of concern or of the candidates for being the maximum and minimum would be points where the derivative is 0, and the endpoints of sort of where are you considering. In other words, what's possible in terms of the range of possible x values. That's it. If you do those, if you can make sort of a list of all those candidates, and there won't be that many of them, then all you really need to do is just investigate each one. You don't even need a graph to do this. You can just have the function itself. Plug them in and check, okay, who's the biggest, who's the smallest? That's it, I'm done. All right? So, so how are we going to do each of these things, right? How are we going to figure out those, right? Who are the candidates? I need a sort of method, I guess, for doing this. Well, the endpoints, the second thing here, those will just be given to you, okay? So, it'll be saying, tell me about the maximum and minimum values on the interval x equals 1 to x equals 7. Okay, then you're living in the interval 1 to 7. So those are candidates. Okay, these will be these will be given to you. Okay, so you don't have to do any work to find those. Now, how will I find these guys up here, points where the derivative is 0? Well, that kind of, I just sort of said it, right? I'm going to be interested in trying to figure out where is the derivative 0, right? That's how I'm going to do it, right? So let me make this clear, though, on the next slide. So, oops, let me go back to my red here. So to optimize a function or a quantity, how should we go about doing this? We need to make a list of all the candidates for who might be a max and who might be the min. Okay, so list all candidates for the overall max and or min. Okay, and that's what we'll sort of officially call these guys, the overall max and the overall min, or the overall maximum, overall minimum. List all the candidates who might be the winner of the highest and of the lowest possible values. And who are these candidates? Well, we just said them, right? So automatically the endpoints of the interval, those are automatically candidates, okay? Because again, you could have something like we saw in our graph in the last picture, where does this graph have its overall smallest or lowest value? It happened to be at like basically at the end, right? It just sort of gets cut off. Now, of course, probably this graph just keeps going down and down and down, and it gets even lower and lower. But that's if I'm living in the world from x equals a to x equals b, then b is my cutoff. So, but in any case, that would be the minimum in that situation. Okay, so the endpoints are in. And okay, I include this endpoint over here as well. Okay, I mean, that's not going to be the winner, right? That's not going to be the maximum or the minimum. So it's just going to be nothing, right? But I'm going to include that as a candidate at the very least. And again, what do I mean by candidate? I kind of just mean, just from a very basic perspective, where did your eye look and check when you saw this graph 20 minutes ago? I think it looked for the peaks and valleys, and it kind of looked at the two ends. And then you did a little bit of just visual comparison in your brain, and you came up with, oh, okay, that's the overall biggest and that's the overall smallest. But you didn't look at a million points. You just really looked at these four for the most part. Okay? Anyway, so the endpoints are candidates. So let's make a little list, right? And literally that's what we're going to do is make a list, just a little chart. Okay, and then who else are candidates? Are these peaks and valleys, right? Which I've already reminded you of, right? So anytime we have a peak or anytime we have a valley, that could also be the answer to the question, where is this the highest or lowest? Okay, so in other words, these guys, right? These points where the derivative is 0, these are candidates too, these peaks and valleys. Okay, So these have a fancier name, which I'll give to you here. So we also want to check for the local, these are called local max and min. Okay? So again, the question of optimization is we're trying to find the overall max and min. In other words, you know, where does this have its overall highest and lowest values? Well, local max and min is a good name because local, what does local mean in English? Just means sort of close by, right, or in the neighborhood. So the local max and mins, what are these? These are the so-called peaks and valleys. Okay, so it's just a fancy word. Local max, local min. Local max refers to peaks. Local min refers to valleys. Okay, and how did we say we were going to do this? We were going to find these. How do we find the local maxes and mins? Well, these are the points where the derivative is 0. Because remember, right, that was what was special about the peak and the valley over on my other graph is that the slope was 0, right? The graph is flat at these 2 points, and only these 2 points, right? Look at the rest of my graph. I know it looks like a complete disaster by now, but nowhere else on this graph do I have a flat top, right? Nowhere else do I have a horizontal slope. So those are my only 2 candidates for, and those are the only 2 local max and local mins that I had. So that's all I needed to consider. Okay? So, so how am I going to figure out where those are specifically? Well, these are points where the derivative is 0, right? That's what makes it a peak or a valley, right, is that it's flat. So how am I going to compute them when I'm trying to do my little chart, candidate chart here? Well, how will I find these? Well, to find these, what should we do? Well, if I take the derivative of the function, which we know how to do that, okay, of whatever we're trying to work with here, of our function, f of x. Okay, we know how to do that, so we'll get some expression like you've done all semester. And then if I want to know at what x value or values is the derivative 0, if I take the derivative, that gives me f prime, right, or the derivative of f. So then I'm just going to set it equal to 0. So set the derivative equal to 0. And solve for x. Okay, if I want to know when is the derivative 0, then make it equal to 0 and solve for x. That'll give you the x values where the derivative is 0. And those are my peaks and valleys. All right? So solving for x there, that gives me these, right? So that gives me the peaks and valleys. All right? So those also are candidates, so they'll go in my little chart also. But once I'm done with these, with this, I have all the possible candidates that I might have. Oh, and you might have more than one here, right? So when you do this, when you find the local max and min, you may have more than one. You may have 2, 3, 4, however many. We'll try not to make it too bad for you. But once I find those candidates, then I don't have much more to do. On my graph over here, which, sorry, is now completely covered in stuff, but after I've sort of figured out, okay, that's a point that I'm interested in, and that's a point I'm interested in, and that's a point I'm interested in because it's an endpoint, and that's a point I'm interested in because it's the a local minimum, right? How did I finish the answer to my question of where's the overall max min? Was I just sort of said, well, all right, if I identify candidate, 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 okay, forget about this part over here. So, all right, I got 4 candidates. Well, which one of these is the overall maximum or the overall highest? Now, again, with the graph in front of us, there's literally no work. I can immediately just sort of zoom to that one and say that's the overall highest. And with a little bit of just squinting, I can pretty much zoom to that one and say that's the overall lowest. Well, what did I really just do there by looking at the graph? Wasn't I just looking for what has the highest y value, right? Remember, of course, that's the y-axis there. So what was it that I was really looking for? Of my 4 candidates, in order to crown the overall maximum and overall minimum champions, all I really need to do is just say, okay, which of them has the highest and lowest y values? In other words, take the x value that's here, whatever that turned out to be, and run it through the function, and do that for each of them, right? I have 4 x values, 1, 2, 3, 4. Run them all through the function, and that'll give you the y values. Okay, well this guy, when I run this guy through the function, he gives me the overall biggest number, so he's the overall maximum. When I plugged this number in, I got the overall smallest number, so that's the overall minimum, and that's the end of the story. These two guys on the left here, these other candidates, they were candidates, right? They were viable candidates, but they would not have turned out to be, when I plugged in this point, for example, I would have gotten a number that was below this point. So this guy didn't win. And when I plugged in this guy, I would have gotten a number that was above this guy. And so that guy didn't win either. And by win, I mean being the smallest. So these two guys were crowned the overall highest and lowest. And so I want to do the same thing in my general sort of strategy chart here of how am I going to do this. Well, step 1 is to get all your candidates organized. And then step 2 is pretty simple. I'm going to plug each candidate into my original function, f of x, to find the overall biggest and smallest. I mean, it really can't, it couldn't be any easier when you get to the end. You're just going to plug stuff in and see what's the biggest number you get. That's the maximum. Whatever the smallest number you get, that's the minimum. And that's the end of the story. Okay? So what's sort of, I don't know, magical isn't quite the right word, but what's nifty about this is that it does give you this strategy, which you see on the slide right here, is not that hard. It won't be that hard to do, number one. And number two, it actually does pretty impressively answer a question that half an hour ago, when I first posed you this question, flash back a slide or two, this one, right? Here's a function. Could you tell me where it has its overall highest and lowest values? Well, we were kind of SOL in terms of just guessing and checking, I guess. Maybe that's how we would have done it. You might have been smarter and said, oh, well, let me make a graph of it, and then at least I have a picture to look at. That makes it easier to find the biggest and lowest values. That's true, it does. But in any case, you kind of don't really, it's pretty hard to do this unless you have a strategy. And the strategy we came up with in the last half hour is pretty easy. And if I just do these steps, right, and hopefully it makes sense why these steps work and why this is a good strategy, it really cuts down on any guessing, right? You get a little bit of guessing, right? Because here we're making a chart of candidates, which obviously sort of implies that they're not all going to be involved, that some of them are going to lose, so to speak. But in any case, it really makes it makes a very difficult problem quite manageable. Okay, so let's see if we can do just a numerical or algebraic example first, and then we're going to sort of immediately be more interested in in word problems, right? In saying, all right, well, I don't really care about being able to do this for a stupid example. How about a real problem where I want the maximum and/or minimum actually means something to me? And that's really what most of the problems in this unit are going to be focused on. But before we do that, an algebra one first. Okay, so let's say we want to say find the overall. Sometimes you use the word global instead, but I think I used overall before, so I'll stick with that. So find the overall max min of this function on the interval x equals -2 to 4. Okay, so we've got a function here. This is a real one now, so it's an actual function. And the question is, could you tell me where does this have its highest and lowest, right, or maximum and minimum value on the interval x equals -2 to 4? So in other words, we're only looking in the window x equals -2 to x equals +4 for whatever reason, right? Okay, so I could draw a graph of this, and it's not a terrible idea, but let's say we want to just sort of fly blind and not do that, just from the context of, you know, a graph is nice because it kind of helps motivate why we're doing stuff, but it's also, you don't always probably want to have to make a graph, right, in order to answer questions. So, but yes, this is a function that has a graph, and if you looked at it, it'd be sort of a wavy thing, kind of like the one that I drew and made up 10 minutes ago. So, but in any case, let's just go. Let's just see if we can figure out what's the overall max and min of this function on this interval. So in order to do that, I'm going to try to just maybe follow my idea here of saying, all right, list all the candidates. So step one, list all the candidates, which should be the endpoints, and then also these so-called local maxes and mins. In other words, the peaks and valleys, or also these are the points where the derivative is 0. Okay, so let's make a little chart. So here's my function, f of x over there. I'm going to make my chart kind of on the right here. So here are my candidates. Okay, and maybe I'll do it this way. I'll make a little chart. X values and y values, or f of x, right? F of x is the same thing as y. All right, so right off the bat, I immediately have some candidates staring me in the face because we just said the endpoints of the interval, right? These are candidates that you should at least consider, right? When I'm trying to figure this out, at least consider the endpoints, right? Wherever the interval starts and stops. So I've got 2 endpoints here, -2 and 4. So I'm going to include those. Those are in. But I might have other candidates too. So where else could the max min occur? Well, the other places of interest are these peaks and valleys, these local maxes and mins. So those also need to be candidates. Well, those I have to work for, right? How do I figure out the peaks and valleys, or how do I figure out where there are peaks and valleys? Well, remember, the idea here is that what's so special about a peak or a valley is that it's flat. And flat to us means 0 slope, or that the slope is 0. And for us, slope is derivative. So how am I going to figure out these guys? First, let me take the derivative, and then if I set it equal to 0, that's going to be, and solve for x, right? These x's I get are going to be precisely the peaks and valleys. Okay? So it's pretty simple. Let's see what we get. All right, so I'm going to find the local max mins. So let me take the derivative of this function. And now here's where hopefully the time that we've spent learning derivatives makes this process quick. But I'm using derivative shortcuts here, right? So 2x cubed, if I take the derivative, I think you get 6x squared. And then minus 3x squared, I think that turns into 6x. And then 12x, negative 12x turns into just -12, because the derivative of x is 1. And coefficients just come along. Okay, so hopefully that isn't a tripping point for anybody at this point of the semester, but if, so there's the derivative. Do it slowly if you need to. All right, now I took the derivative, and again, that's an expression that now gives us the slope, right, at any given point. Well, the question here to find these local maxes and mins, these peaks and valleys, was I was actually interested in when is the slope 0, right? That was the whole point, is that was going to be my peaks and valleys, right? So as soon as I take the derivative, the next thing I want to do is set it equal to 0. Again, because I'm looking for where is the graph flat. Okay, so now my question is this, right? When is that true? Okay, so here's where in all of these problems, including the word problems, this is where algebra is your friend or enemy, or frenemy, I guess as the case may be, in terms of it's your friend because algebra is what you need now in order to finish. It's your enemy because here's where, unfortunately, we can run into some creative algebra, i.e. algebra mistakes, that then lead you to the disastrously wrong answer. So be careful here and try to use your problem solving, your algebra skills appropriately here. So, Okay, so I want to solve this. I want to say, when is this true? Tell me the x values for which this is true. Now, hopefully you have enough intuition that this jumps out at you as something that looks like maybe you could factor it. Or at least, you know, that it's the type of thing that we might factor. But I'm going to first actually just divide everything by 6, because I see I can do that, right? Everything has a multiple of 6. So I'm going to divide everything by 6 just to make it nicer to look at. When you divide 0 by 6, you just get 0, so that's good. And now, hopefully, this is screaming at you, not so much just a whisper, but an actual scream, to say, oh, that factors pretty nicely into that. Okay, now if it didn't factor, right, this is where you use quadratic formula, which you may have to use for some of these problems. But this one I rigged so that it would work out, all right? But in any case, this answers the question, when is this true? And remember, it's at the opposites of these. So it's at x equals positive 2 and negative 1. Okay? So what this means is that you have local maxes or mins, or peaks and valleys, at these 2 points, x equals 2 and x equals negative 1. The graph hits a peak and hits a valley at those points. Okay? So those represent, one of them is sort of looks like that, and one of them kind of looks like that. Okay, and they're candidates, right? I don't know if they're the winners yet, but they're at least they're certainly candidates for those might be the overall max or mins. But that's it, right? Okay, now I know this one also has 4. It doesn't always have to be 4 candidates. There could be more or less than 4. But okay, fine. I don't have any other x values where this is true. That's it. I did that. So this is it. So I've got 4 candidates here. And it couldn't be any easier. It's a little tedious right now. But what is it that I have to do to now finish is I'd say to myself, all right, I did this step. I got all the candidates. So I have to crown the winners. So how do I do that? Just check them, right? This is not a sexy process where I have a great strategy here. I'm just going to check all of them. So here's my candidates. I got 4 of them. And now I'm going to run them through the function and just say, okay, well, where is, what do I get? What do I get when I plug this in? In other words, how high or how low are these guys? So I'm just going to plug, in this case, negative 2 into the function up here, right? That's f of x. So I'm going to plug negative 2 in. And I did all of these already, so I'm going to save myself some time here. And I think if you plug in negative 2 into the function, you get negative 4. If you plug 4 in, you get 32. If you plug 2 in, you get negative 20. And if you plug negative 1 in, you get 7. I think my math is right there, but so when I get to the end here, I say, all right, so what's my final statement? Well, I had 4 candidates to be the overall high, low, or max, min, and I checked each of them, and I figured out just how high or low each of them went. So now I just say to myself, okay, well, if I pick the largest of these numbers, that's going to be the overall max. If I pick the smallest of these numbers, that's the overall minimum. And now it doesn't take much effort to find out. 32 is the biggest number I see, so the overall max, it must be there, is at 4, right here, is 4 comma 32. Right? That's the point, if you want to say that. And then the lowest that this goes, negative 20, right? Negative 20 is the smallest, or the lowest number I see. So the overall smallest is at 2 comma negative 20. Okay, and so moral of the story, in this case, actually, the overall maximum turned out to be one of the endpoints, right? 4 was one of the endpoints. But 2, that wasn't an endpoint, right? That 2 came from that being a local minimum, I guess, as it turns out. So that was a valley, right? And then the other 2 candidates, right? Negative 1, which was a peak, that turned out to not be high enough. and -2, which was the other endpoint, right? -2 is the other endpoint. That turned out to not be low enough to be the overall minimum, right? So anyway, it doesn't really, you don't have to tell that story at the end. You just want to get the answer, what is the highest and lowest, and that's it. And we did it. And again, I have to say, it's kind of not a groundbreaking, like, oh my God, this person who figured this out is a genius, kind of a strategy. But it's pretty good. It's pretty good in that it's compact. It's pretty easy to reproduce and do every time. And not a whole lot can go wrong. And now I'll speak more so for you guys and for people doing these problems. The only real place you're going to probably go wrong is maybe with the algebra step. Sometimes it's factoring, like this one. Sometimes it's just other sorts of algebra problem-solving things. So just be careful in this step. I guess I probably will say that about 1,000 more times, but that's really the only place that we really even did any real math besides just arithmetic. So, okay, so I'm going to end this video now. This is the algebraic example, or the sort of just a symbolic example. What's next will be what we really care about, which is doing this process, but doing it for word problems, where the setup is not, here's a function, I already give it to you, now go. It's, here's a whole bunch of words. You have to come up with this. Okay, that's much harder. Okay, so we certainly need lots of practice with doing that, and that's what the next video will start us with.